Welcome back to IB Chemistry Stoichiometry. We're going to continue with where Brittany left off and talk about concepts 1.3. We're going to talk about reacting masses and volumes now. Okay, so before we jump right in, let's start with a small problem that's going to represent what we'll be doing next. Imagine that we have 8 car bodies and 48 tires. How many complete cars could we make? Well, each car needs 4 tires, so 4 tires times the 8 cars we need to make means we'll need 32 tires. Which means we can successfully make all 8 cars, but we're going to be left with 16 extra tires. This is a simplified example of limiting reactants and excess reactants. In this problem, we are limited to making only 8 cars because we only have 8 car bodies, which leaves us with an excess of tires that have remained unused. So, what are limiting and excess reactants? A limiting reactant is the reactant that limits the amount that the other reactant can combine and the amount of product that can form in a chemical reaction. The substance that is not used up completely and remains in excess is called the excess reactant. So for example, let's say you have fire and wood burning. The wood is the limiting reactant here since the fire can only last for as long as there is wood, while the excess reactant is the oxygen that's being consumed from the chemical reaction, which we have excess of. Okay, so let's do a problem with limiting reactants. Let's say we have barium chloride and it's going to react with potassium phosphate as follows. 3BaCl2 plus 2K3PO4 is going to become 6KCl plus Ba3PO4, 2. Calculate the mass of barium phosphate that could be formed when a solution containing 10 grams of potassium phosphate is added to a solution containing 12 grams of barium chloride. We're going to go ahead and take the molar mass of each of these compounds. So the molar mass of potassium phosphate is going to be equal to 212.27 grams per mole. The molar mass of barium chloride is 208.24 grams per mole. And the molar mass of barium phosphate is 601.96 grams per mole. Here the mole ratio is 3 moles of barium chloride to 2 moles of potassium phosphate. While there are more moles of barium chloride than there are potassium phosphate, it's not 1.5 times greater. Therefore, barium chloride is the limiting reactant and all other calculations will be based on barium chloride. Also, since we have our limiting reactant, we can conclude that potassium phosphate is therefore the excess reactant. So next let's talk about theoretical yield. Theoretical yield is the maximum amount of product that can be produced from a given amount of a reactant. It is the ideal amount of product that can form from a perfect stoichiometric calculation. This means that none will be left behind and every single bit of one compound will be transferred into the product. On the other hand, we have experimental yield. Experimental yield is here because the world isn't perfect. We have many variables that can't always be accounted for when conducting a reaction, and so when we go and conduct a reaction as chemists, we don't always end up with a perfect amount of product that we get from a certain amount of molecules. This is why we have experimental yield. Experimental yield tells us how much of an actual product has been received from a reaction containing a certain amount of reactants. And the concept that unifies both the experimental yield and theoretical yield together is the percentage yield. Percentage yield is the experimental yield divided by our theoretical yield multiplied by 100. This is used to show us just how much variation the chemist was from the perfect theoretical yield. So let's do an example problem with percentage yield. Let's say that there's a bag of popcorn with exactly 100 kernels in it. In a perfect world, 100% of those kernels would become popcorn, and then we would therefore have 100 pop kernels in our theoretical yield. Now if you went out and you took one of these bags of popcorns and you came back with only 80 pop kernels, leaving only 20 behind, the experimental yield here would be 80 pop kernels. The percentage yield would be 80 of our experimental yield divided by 100 from our theoretical yield, which times 100, which gives us 80%. So now let's talk about Avogadro's law. Avogadro's law is an experimental gas law relating the volume of a gas to the amount of substance of the gas present. This can be written as V over N equals K, where V is the volume of the gas, N is the amount of moles of the gas, and K is a constant equal to RT divided by P, where R is the universal gas constant, T is the temperature in Kelvin units, and P is pressure. This law is used to prove that V1 over N1 equals V2 over N2, volume 1 divided by the number of moles in the first gas is equal to the volume of the second gas divided by the number of moles in that gas, which means that the molar volume of an ideal gas is constant at a specified temperature and pressure. Common rearrangement of this formula is PV equals nRT, which you might recognize as the ideal gas law. This law describes how, under the same conditions of temperature and pressure, equal volumes of all gases contain the same number of molecules. So now let's do an example problem with Avogadro's law. Let's say we have 5 liters of a gas, and it's known to contain 0.965 moles of that gas. If the amount of gas is increased to 1.8 moles, what will be the new volume, assuming that the temperature and pressure remains unchanged here? Well, since we have our volume and the number of moles, and we know that our temperature and pressure have remained unchanged, we can use the equation V1 divided by N1 equals V2 divided by N2. Substitute our numbers here. We'll have 5 liters divided by 0.965 moles is going to be equal to X, which is the volume we're trying to find, divided by 1.8 moles. So now we just solve our X, take 1.8, multiply it by the other side, get a final number, and that final number will be approximately around 9.33 liters. So our next concept is solutions in stoichiometry. Many times we have reactants and products that are chemical reactions that happen inside water or other aqueous solutions. In these cases, the concentration of the solution must be determined in order to determine different amounts of the reactants or products. This is where we use the concentration of a solution, and it's the measure of the amount of solute that is dissolved in a given amount of solution. This is where molar concentration, also called by its most common name, molarity, comes in to help us. Molarity is defined as the moles of the solute divided by the liters of the solution, and this is what we use to determine how much of a concentration of a certain reactant or a certain product there is in a solution. So, simple enough of a concept, let's go ahead and apply it. Here we have an example that will help us use molarity. Suppose we had 1 mole of sucrose, that's about 342.3 grams, and proceeded to mix it into some water. It would dissolve and make sugar water. We keep adding water, dissolving and stirring until all the solid was gone. We then made sure that when everything was well mixed, there was exactly only 1 liter of the solution. What would be the molarity of this solution? The answer here is 1, since 1 mole divided by 1 liter is going to give us 1, and that's our molarity, 1 mole per liter. And our last but certainly not least concept in stoichiometry is standard solutions. A standard solution is a solution containing a precisely known concentration of an element or a substance. A known weight of a solute is dissolved to make a specific volume here. Standard solutions are used to determine the concentrations of other substances, such as a solution in a titration. The concentration of a sample solution can be found usually via Beer's law. Thank you so much for watching, everybody. I hope you learned a lot, and have a nice day.